In this lecture, we will introduce why moisture can be a problem for facade design engineering, and we're gonna look at the so-called condensation risk. First of all, what is moisture? Moisture can occur in three states. One is ice or snow, so solid. This could be deposited in a facade because of snow or because of temperatures going down in winter, and this can cause damage. Of course, also because this can melt and becomes water, which is the principal enemy of a facade in terms of water tightness, and it will provide damage but also increase the growth of mold. And in the third state, it's moisture. Moisture in vapor is also dangerous for facades because when it touches a surface of a facade that has the dew point temperature, it will condensate and become water again, but also because traveling across the facade, even worse, might condensate across the facade and create interstitial condensation. So it's mandatory that we design constructions and facades that keep for the majority of the time in a year dry, and therefore decrease the risk of mold growth and condensation. We're gonna now have a better look to how to do this. So first of all, how much moisture can the air contain, and when is it that the moisture in the air condensates and can become water? So this depends on the temperature of the air. Let's have a look to this chart that you can see in this slide. This is the so-called psychrometric chart. It's a graph that has in the x-axis the dry bulb temperature, so the temperature of the dry air. And on the y-axis, we see the humidity ratio, so the amount of vapor per amount of air that is contained in the air. As you can see in this graph, depending on the temperature, you may see different levels of relative humidity. In other words, if we see the top line, this is the condensation line, so it's the line where the relative humidity is 100%. This means that if there is moisture and the air is in this state, it will condensate. It's 100% humidity, it's water. As you can see, this line is not constant depending on the temperature, but it decreases with temperature of the air. This means that the colder is my air, the lower is the amount of moisture that the air can contain, because the easier is to condensate. You can see this because I need very little moisture content to have condensation. Instead, if we go towards the right, we will see that the hotter the temperature of the air, the higher the amount of moisture that the air can contain. So this graph is very useful because it shows us something very important, that depending on the temperature of the air, there is going to be a maximum level of moisture that the air can contain before it starts to condensate. This is something that we know in our daily experience. Remember, like in winter, when, for instance, you step outside and you feel the air much more humid than indoors, maybe because the temperature of the air is lower, and therefore you feel the relative humidity higher. But for instance, in summer, when we try to cool down air, because we want to, for instance, use an air conditioning, the air conditioning system takes air from outside, which has a certain relative humidity, and cool it down. In cooling down the air, often we have condensation, and this is why air conditioning systems usually have to have a condensation accumulation and a water drainage. This is very normal, and this is very important, and we can test and assess where we are by using this graph. Let's go back to the facade though. Why this is important? So, depending on the U value, you're gonna have a different temperature across the facade. So, for instance, if we have a good facade and outside is 0 degrees and indoor is 20 degrees, we know that the facade will have this temperature range across its sections because it is insulating, it's creating a temperature difference between outdoor and indoor. This means that if air is traveling from inside towards outside across the facade, and this can happen because there is a pressure difference between indoor and outdoor, therefore the air is pushed through the facade. This can happen because there might be leakages, which creates very easy channels for the air to travel. Or there are many other different ways why moisture and air travels across the facade, as you can see when looking at the air tightness of an envelope. So, regardless of how, the air can travel across the facade, but hotter air from indoor will travel towards increasingly colder sections of the facade, and it will lower its temperature until it reaches outside. This means that either on the inner or outer surface or across the facade, condensation may occur simply because the air that was okay in a certain temperature when traveling towards the outside in winter will become colder and may reach the condensation temperature. Let's have a clear look to the equations that can help us to see why this is happening. So, the law of Boyle-Gay-Lussac that you see in this slide is telling us something very important. The pressure of a gas in a volume depends on 4 parameters. One is the famous R, which is the constant of gases, so it's a constant. T is the temperature, as we saw before. And then we have M over V. M is the mass of moisture, while V is the volume. M over V is the density. So when condensation occurs, we could say that M over V is 100% relative humidity, which means that the maximum pressure that the air can sustain from the moisture being inside the air is defined in this equation by placing M over V equal to 100. So you have, as you can see here, 100 RT. This is the maximum pressure, and this is the so-called pressure of saturation. So it's the pressure where the air will condensate, the moisture in the air will condensate. So the relative humidity, in fact, is defined as the ratio between these two pressures, as you can see in this slide, times 100. Now, it's important we distinguish two cases. Moisture can condensate on the surface of the facade or across the facade. The first one is called superficial condensation. This is something very common, and you can see it often when, for instance, you're taking a shower, you're creating a lot of vapor, and you see moisture and water in the surfaces like mirrors or windows. This is because those surfaces are colder than the air in the room and therefore cannot take so much moisture, which is quite rich because you might be showering at that moment, and it condensates on the surfaces. This also happens in facades. Typically, when we see a poorly performing facade, a facade that has a high U value, which means that heat can travel very easily, you may see condensation on internal surfaces because the surface of the indoor facade is very cold in winter for sure. So superficial condensation is the first class. The second class of condensation is called interstitial condensation, and this is what we call when the condensation is occurring across the layers of the facade. Now, there is some standards and regulation provide a very simple method for superficial or surface condensation, and it's the so-called temperature factors. You may be in a country where the local regulation tells you what is the maximum temperature factor that you can have in your facade. This means looking at your facade in steady state, so not in a dynamic regime, but in a steady state condition, for instance, considering 0 degrees outside and 20 degrees inside, looking at how temperature vary across the facade, and then some regulation tells you the ratio between the temperatures across the section minus the external temperature, so TIO in these slides and TE, the external temperature, over the internal surface temperature TI minus TE, as you can see in these slides. This ratio can usually be only around 0.5 or 0.65, depending on the country and the type of building. And this is a simple check that you can do to see if you're gonna have surface condensation, typically in winter, on your facades by checking these temperature differences. Of course, there are more sophisticated calculations you can do by having a dynamic understanding of how temperature fluctuates in time and moisture levels. Because of course, these are not static. They will depend on what happens in your building. If you're having a party and many people are inside the room, they will produce a lot of vapor, of course, higher in the risk of condensation. But this can also happen because depending on the outdoor weather, we have different relative humidities depending on the weather. So the problem is dynamic. In fact, many regulations don't impose a rigid limit, but also ask you to check if in the majority of the time of the year, if there is condensation, this moisture is drying up or not. So some condensation may allow if in summer the assembly gets dry. Interstitial condensation is a bit more challenging to assess because, of course, requires an understanding of how temperatures and pressure levels are varying across a facade. Let's have a deeper look together. There are 3 steps we need to do to assess interstitial condensation. The first one is to know how temperatures varies across a section. What is the progression of temperatures across the section? The second one is to know what is the maximum vapor pressure, the Pmax we saw before in the previous slides, for a certain given temperature. And now I will show you a very easy method, which is a graphic method, which is based on Glaser methodology. A typical solid construction with an external insulation layer. So this is the insulation, this is the brick wall. So if we imagine it's winter, so outside it's 0 degrees and inside is 20 degrees, and we have a relative humidity of 80% and inside 40%, we are able to also to define 2 things. First of all, the temperature progression. So here it's 0 degrees, so then the insulation has a very good thermal resistance, so the line is very sharp and inclined. Then the brick wall probably has a lower thermal resistance, so you can see the line becomes more horizontal, and then it meets the 20 degrees. This would be typical temperature progression on a solid wall, with this being the temperature externally and this being the temperature internally. So this is Ti and this is Ti. Now, because we know from the law of Gay-Lussac that the pressure that the air will have is equal to the density, the relative humidity, M over V, times R times T, T be in Kelvin, we can also calculate the maximum pressure, the pressure of saturation that you have externally and internally. In this case, for instance, if I do this calculation, here I have 208 Pascal, while here I have 936 Pascal. Of course, the higher the temperature and the lower is the relative humidity, but the pressure becomes higher, which means the pressure of saturation is higher, which means it's more difficult to condensate. I have to reach a higher pressure. This is very important and it will now help us to understand if it condensates or not, because the same way we draw the temperature progression, I can draw the pressure, the maximum pressure progression being here. I'm gonna draw it here. For instance, we start from 208, and then in the same way the temperature change, we're gonna have the progression from 208 Pascal to 936. So you can see that the warmer becomes the layer, the higher is the pressure of saturation, and therefore the lower the risk of condensation. But of course, the air with moisture, because it's warmer inside than outside, will travel in this direction usually. So what we need to see is that if, while the air is traveling across the facade, is in any point condensating. So if I was to draw now what is the missing link, is the so-called calculated pressure. So the pressure of my air, which will be always following this law, and it will depend on the relative content and the temperature. Of course, we know this because we know that the absolute amount of humidity of moisture doesn't change. The earth is not receiving any treatment, so it doesn't change, and the volume either. So we can calculate the calculated pressure. And in a case where condensation doesn't allow, you will see that your pressure is always lower than the maximum pressure of saturation. You see the black line never meets the purple line. Let's do now an example when there is interstitial condensation. So what happens when condensation occurs? We have a wall. Let's take now a solid wall for simplicity, and we can draw again the maximum pressure of saturation. That will do something like this, no? And for instance, if we take the case before, you had 208 Pascal outside, 136 Pascal outside. So we can imagine that we start with a calculated pressure that is below the saturation pressure, because there is no condensation inside the room, and then the air starts to travel across this facade. And if at some point, when the pressure and the temperature change in the room, the line of the pressure calculated cross the maximum saturation pressure line, condensation occurs. And this means not only that we know where it's occurring, because we know for each of these points what is the calculated pressure and the maximum saturation pressure, because we know the temperature, but also how much condensation will occur. With this simple method, we are able to address in simple terms the risk of interstitial condensation. Of course, this is a simplified method that takes into account a steady state behavior. In a more complex phenomenon of you are looking at a yearly performance, you may have to do dynamic simulation of hygrothermal behavior. But now, to start, this is an efficient method to get you started with your facade design assignment.